Today I will discuss the topic of directional derivative. What is directional derivative? This is very important topic of vector calculus. See, first before going to directional derivative, I'll give you a brief idea what do you mean by derivative. Derivative of one variable. We have read it in derivative of function of single variable. See, this topic, we had this topic in differential calculus. Suppose I have a function y equals to fx. Suppose I have a function y equals to fx. Y is a function of x. Fx is a function of single variable. So this can be plotted on xy plane, right? Fx can be plotted on y-axis. It can, let's say, it is plotted like this. Let's say this is how the function is plotted. Y equals to fx. So what does the derivative of f dy by dx signifies? What does this derivative signify? What do we mean by dy by dx? See, dy by dx signifies the rate at which the function vary when we vary x, rate at which y vary when x is varied. Here x is independent variable and y is dependent variable. Y is depending on x by this function. So this dy by dx tells you how the function varies with respect to the variation in x. Geometrically it represents, suppose I want to find dy by dx at point say x over here, then dy by dx represent, if I draw a slope, dy by dx gives you the slope of this tangent. The slope of this tangent gives you dy by dx gives you the slope of this tangent. If the slope is higher, it means y is increasing rapidly with respect to an increase in x. So say if we have two things over here, sign and magnitude. If f dash x is positive, the sign signifies whether function is increasing with increase in x or function decreasing with the increase in x. So if f dash x is 0, it means the function increases with increase in x. It means when I move along x-axis, y increases. When I move along x-axis, the value of y on this curve is increasing. So if f dash x is less than 0, it means the function fx decreases with increase in x. Means we also call it fx is a decreasing function. The graph will be something like this. The graph will be something like this. The y value of, as you go towards increasing x, the value of y decreases. Value of y is falling over here. So that means the function is decreasing. F dash x is negative. You can see over here. Here, see theta, the tangent makes an angle theta with the x-axis. Here you can see if I draw a tangent, it makes an angle negative. If this direction is taken as positive, this direction will be taken as negative. It can be say minus pi by 4 or minus pi by 3. So the slope is negative over here. The angle theta is negative, so tan of negative theta will be negative quantity. So we say the slope is negative or the derivative of function is negative. So the sign signifies whether the function is increasing or the function is decreasing. What does the magnitude signify? The magnitude signify the rate at which function varies with the variation in x. Means over here if you find the function is the tan theta is less, the tan theta is less. Here you see tan theta is more. It means function is increases rapidly over here with increase in x. Function increases slowly over here with the increase in x. Suppose I take delta x over here, then you can see the variation in delta y is only this. But I take the same delta x over here. If I vary x over here, you find the variation in y. This is the variation in y, delta y. Right, so the function increases more rapidly at this point, function increases less rapidly over here. Dy by dx is less dx. Over here dy by dx is very high. Over here dy by dx is very high, it tends to infinity, right? For a small increase in x, y is increasing rapidly. Alright, in the same way you can see that in this case over here your dy by dx is very much negative. Over here the magnitude of dy by dx is very high, means function decreases rapidly with the increase in x. Over here function is decreasing slowly with the increase in x. So dy by dx is highly negative over here, dy by dx is very less negative over here, near to 0, right? So the magnitude of f dash x gives you an idea about with what rate function increases when x is increasing, right? So, or with what rate function is decreasing with an increase in x. So the magnitude gives you, the magnitude of f dash x gives you with what rate, how much high is the rate at which function is increasing or decreasing with the increase in x, whereas sine gives you an idea whether the function increases or decreases with the increase in x, whether the function is increasing or function is decreasing. This is what we mean by derivative of function of single variable. See, the domain of a single function of single variable, either it is the whole x-axis or it is part of x-axis. Like if you have y equals to say root x, the domain of such a function is the positive x-axis, right? If I have say equals to 4 minus x squared, domain of this function will be a region between -2 to +2. That is the domain of this function. Only for x varying between -2 to +2, your y is a real, y is defined. So you have the domain of this function will be from -2 to +2. So what do you find? You find that the domain is either part of x-axis or it is the whole x-axis. The derivative gives you how much, with what rate the function changes, with what rate y increases or decreases when you are moving along x. See, the domain over here is one dimensional, so you can move only along x. You can move towards positive x or you can move towards negative x. So, and when you move along positive x or you move along negative x, this particular quantity gives you an idea when you move along positive or negative x with what rate your function, with what rate fx is plotted on y-axis, with what rate the function increases or decreases when you move along x. There is only one chance, we can move only along x, either towards positive x or negative x. But the scenario changes when we are talking about function of two variables. Now let me move to the function of two variable and understand the notion of what is meant by derivative of the function of more than one variable. Let's take function of two variables, then I'll explain to you about the derivative for the function of three variables. So let's try to understand the derivative of a function of three variables. See, the derivative of a function of single variable is pretty easier because the domain is one dimensional. One can move only along x and see how y is varying. One can move along x and see how y is varying. If y is varying rapidly, we say the derivative is very high. If y increases slowly, we say derivative is small. Now let's move to the function of two variable and see what the derivative of the function of two variable mean. So let me take an example of the function of two variable. Let me rub all this, right? Now I'll proceed towards the function of two variable, right? If I have any doubt, we will learn in detail about this function of single variable in our differential calculus. Now let's move to the function of two variable. All right, suppose we have a function of two variables. Suppose we have a function fxy. Suppose we have a function fxy. Let's say fxy. Suppose we are taking an example. Suppose fxy is x square plus y square. So if I plot this function on z-axis, first of all, before plotting it, I would like to make it very clear what is the domain of this function. For what value of x and y this function is defined. You can see the function is defined for all the value of x and y. So I can say, if I am asked about the domain of this function, I'll say the whole xy plane is the domain of this function. Here x and y are independent variables. X and y are free to vary. For every value of x and y, your fxy is defined. Suppose I take an example of, say, fxy equals to, say, under root 2 minus x square minus y square. In this case, the domain of the function is a region enclosed by a circle of radius root 2. You can see it over here. The domain of this function will be x square plus y square less than root less than 2. It can be a region which is enclosed by a circle of radius, say r equals to root 2. This is the domain. This is the domain of this function. So what I want to say is, the domain of function of two variable, the domain of function of, when I say variables, I mean real variables, real functions. Domain of function of two variables, it is either whole xy plane or part of xy plane. Either it is whole xy plane or part of xy plane. Now let me proceed ahead with this function fxy equals to x square plus y square. Let me plot this first. Let me plot fxy on z axis. X and y are independent variable. Z will be a dependent variable which will be given by z equals to fxy. Let me plot this. What is this actually? What exactly is this? This is a paraboloid. This is a paraboloid. It looks like cup-shaped object, cup-shaped surface. I'll draw it for you. The function can be plotted like this. This surface is a surface of a paraboloid. This is locus of all those points in space for which the z coordinate is related to x and y coordinate by this equation, z equals to x square plus y square. The domain of such function is whole xy plane. The domain of such the function is whole xy plane. The x and y are independent variables. Z is a dependent variable. Z is a function of x and y. We are plotting the function on z axis. So xy plane, for this case, this function, the whole xy plane is the domain. Now what is the concept of derivative over here? What do you mean by the derivative over here? The function is z equals to x square plus y square. The function is plotted on z axis. So this is the function of x and y. So what do you mean by the derivative of this function? What do you mean by derivative of this function? What did I mean by derivative of a function of single variable? Derivative of single variable just meant how the function changes, how y changes with the variation in x. Here you have two variables. Unlike the function of single variable, here you have a function of two variables. So derivative means how the z changes when you vary x and y, both or singly, or you mean to say the derivative means how the z changes when I change x and y. I can change x only, I can change y only, I can change x and y both. So there can be several possibilities. In fact, even when I say I can change x and y both, x and y can be changed in infinite number of ways. I can change x rapidly, I can change y slowly. Suppose I move along this path. In this case, your y is changing rapidly, x is changing slowly. If somebody moves in this direction, x is changing rapidly, y is changing slowly. If somebody moves along this direction, in this case y is not at all changing, x is changing. If somebody moves parallel to y-axis, your x is not changing, it's only y which changes. So you can see there can be several possibilities of varying x and y. In case of function of single variable, there was only one possibility: either you can increase x or you can decrease x. Either you can increase x or you can decrease x and see how z is varying. But here, since you have a function of two variables, the domain is two-dimensional, unlike the function of single variable where the domain was one-dimensional. Here the domain is two-dimensional, so x and y can be varied in infinite number of ways, right? X and y can be varied in many ways, and these are the just few cases. X and y can be varied in any number of ways. Somebody can move like this also. Somebody can move along the curve. This is how x and y is changing. The curve shows how x and y changes, right? So here we have to understand how z changes when you vary x and y. I rub these things. Alright. Try to understand it very carefully. This is a bit difficult, but you please concentrate on my lecture. You will understand it completely. This is very important. This is not very important from the exam point of view, but this is very important from application point of view. You can apply it at several places in basic sciences. Alright, this is part of applied mathematics. So our task is to understand how z changes when I vary x and y. We saw x and y in the domain can be varied in infinitely many ways. It can be varied in infinitely many ways. Suppose somebody moves along this direction. Somebody moves along this direction, or say we are moving along this direction, let's say, right? So let's say this is dr. This is dr, right? Or to be more precise, let me draw it like a curve. Let's say we are moving along this direction. Alright, we are moving along this direction. This is, say, we are moving along this direction. So we are moving on this curve. We are moving on this curve. Alright, so we can write here, say, initial point. This is initial point, this is final point. This is, say, dr. Alright, we have moved from, say, this is xy, and this is x plus dx and y plus dy. When you move from, say, p to q, x changes by dx and y changes by dy. X changes by dx and y changes by dy. When your x changes by dx, the change in the function is given by this. When y changes by dy, the change in the function is given by this. I hope you have learned partial derivative. df is given by the change in f when x changes by dx, and when y changes by dy is given by this. These are partial derivative. I'll explain to you the meaning of partial derivative later on. So when x changes by dx, this dou f by dou x tells you the variation of f keeping y constant. This tells you the variation in f keeping x constant over here. So df can be written as dou f by dou x dx plus dou f by dou y dy. So this can also be written as I plus j dot dxi dyj. Now suppose on this curve, this is the curve, this is the actual curve along which you are moving. This is a vector from initial point to final point. So on this curve, let's say x is a function of, say, s, length of curve. S is a parameter. Y is a function of s. Alright, s is the length of curve. S is a length of curve. S denotes the length of curve till this point, x and y. So I can write it like this. So in that case, when you are moving along p to q, this length of curve is ds. This length of curve is ds, and obviously your dx and dy will be a function of ts only. The dx and dy will be a function of x. X and y is a function of s. So dx and dy will be related to this ds. I can write this df as df by ds. I can write it over here, df by ds. As I move from p to q and cover this distance ds, this can be written as df by dx I plus, or if I move earlier, I put it over here. I write it as df by dx plus dou f by dy So this can be further written as I plus j dot product dx by ds I dy by ds j, or this can be written as I dou by dou f j dou by, sorry, this is y dot dr upon ds. This is dr. Remember, this is dr vector. So in limiting case, you can understand this ds is nothing but the magnitude, this ds and the length of this dr vector in limiting case. When q tends to p, dx and dy is obviously very small. So the length of this dr vector and the length this ds will be very small. I can add delta r and delta s. In limiting case, the dr and ds is the magnitude of dr. So in this case, since ds is the magnitude of dr, this will be a unit vector. So I can write I dou by dou f plus j dou by dou I f dot, what is this dr by ds? Dr by ds is the unit vector. Obviously, in limiting case, this length of curve and this vector dr is a vector from initial point to final point, right? So this dr, this ds and ds will be the magnitude of this dr. So in that case, your dr by ds is nothing but the unit tangent vector. If you are moving along this, it gives you a vector in the direction where you are moving. You are moving along this direction, so this gives you a unit tangent vector, a unit vector in the direction in which you are trying to see the variation of, or you are moving. It is a unit vector in the direction in which you are moving, and you are trying to see the variation of f. So this can be, say, let's say a vector. This can be a vector. So the directional derivative, when we are moving along the curve and covering a distance ds, this is the rate at which the function changes when you are moving along this curve ds. See, what does the curve define? Curves gives you one way in which x and y is varying. See, x and y is varying in the way such that x is f1s and y is f2s. So curve defines one way. Curves defines the way x and y are changing when you are moving in the domain. There can be several ways in which x and y can vary. There can be several curves along which I can move. So curve gives you an idea about how x and y is changing when you are moving. When you are moving in a domain, you will move in a curve. Obviously, when you are moving in a domain, you can move in either one curve or other curve. You will move in a curve. You will move in some. You will have some path, right? And the path determines how x and y is changing when you are moving in that two-dimensional domain, right? And this gives you an idea when you are moving along that curve, or you say when you are moving along that curve in the domain. This gives you an idea about how the function changes. The function is plotted on z-axis. So this is giving you, I can draw it over here. You can see geometrically also. See, what is f? F is this height, right? This height. So when you're moving along this path, you draw a line, right? This gives you, this is what this length is z, this length is fxy. So you can see it over here, your fxy is increasing. Fxy is increasing when you're moving from p to q along the curve, right? Along this curve, curve determines how x and y changes when you are moving along certain path. So what do? You find that the z is increasing. Right? So df by ds exactly determines how f changes if one is moving along certain path in the domain. So how will you find that? You have to find first this, and then you find out the unit vector in the direction in which you are moving. Unit tangent vector to the curve. At any point, if you want to find out the directional derivative, you just find the curve along which you are moving. You just find unit tangent vector a, that is a unit tangent vector, right? So this can be further written as del f dot a where del f can be defined as, I can define this del f as plus j del f by dy. This is nothing, we call it gradient of f. We call it gradient of f. So if you want to find how the function changes with the increase in x and y, ds just determine the curve, the way x and y is changing. When I'm moving along any curve, how f is changing. This is given by, this is called directional derivative. This is given by the gradient of f dot the unit tangent vector in the direction in which you are moving. So this is called directional derivative, right? This is called directional derivative. Getting your point? The directional derivative. See, why we call it directional derivative? Because somewhere or other you see some kind of directional feature associated, like the rate at which f changes depends on in what direction you are moving, right? In what direction you are moving, it depends on that. You are moving in this direction or you are moving in this direction. There can be several directions in which you are moving, right? So it does depend on the direction in which you are moving. This is a. This is a is the unit vector in the direction in which you want to find the directional derivative, in which direction you are moving, the unit vector in the direction in which you are moving, and trying to find out how does f is changing. So this is a unit vector. That's why the name called directional derivative. I'll discuss in detail, quite detail about this directional derivative still also. Now before I move further, I'll try to discuss with you the significance of these quantities. The significance of these quantities, dou f by dou x and dou f by dou y. These are called partial derivatives. These are called partial derivatives. I'll tell you what is the significance of these partial derivatives. These partial derivatives are nothing but a very special kind of directional derivative. I'll tell you how. So let me first describe dou f by dou x. I'll rub all these things, right? You make a note of it. Let's try to understand the partial derivative of f with respect to x. How do you find it? You write it as df by dx keeping y constant. F has been plotted on z axis. F has been plotted on z axis. So here f was, I'll consider the same function. So I can write, if I plot it on z axis, f is plotted on z axis. So z is x square plus y square. So this surface is the locus of all those points whose z coordinate is equal to x square plus y square. This surface represent this equation. What is this is the relation between the coordinates, which is coordinates of any point which is lying on the surface. All the points on the surface are going to satisfy this equation. Surface is just the plot, the locus of all those points in three-dimensional space, where z coordinate of every point is equal to the square of x and y coordinate, and those points, when they are joined together, gives you this surface. This is a paraboloid. This is a three-dimensional surface. This is a paraboloid. So this is z equals to x square plus y square, right? So what do you find? You are finding that f or z is, since f is plotted on z axis, I am calling f as z. So what do you find? You find that z varies with the variation x, z vary with the variation y also. Z is a function of two variables. Both variation in x and y affect the value of z. If I vary x only, then also z varies. If I vary y only, then also z varies. If I vary both, then also z varies. So what does this gives you? This gives you the rate at which function varies when y is kept constant. How does, see, the natural need of partial derivative arises because we are always interested in when you have some function depending on two components, when you have some function depending on two variables. Like a very practical example I can give you, like your performance in the exam depends on the number of hours you devote to the study and the quality of study, the concentration which you have. So you have two things. One, quantity of study, how much hour you study. Whenever you meet among yourself, you just ask a very common question, that how much you are studying or how many hours you devote to the study. Many students also ask us, sir, how much hour I should study so that I qualify a particular exam, right? Then and somebody tells, sir, I have studied so many hours but still I am not performing well. So you have two factors on which your performance in the exam, say performance is a function. So your performance is a function of your two things, one quantity of study, that hours of study, and other quality of study. Some people study for long duration but still they don't perform well because they somewhere lack, their study somewhere lack in quality. They are studying and read the book of mathematics and then think something else, then that won't give you a good performance. So performance has dependence on quantity, performance has dependence on quality also. So when you are interested in knowing how much performance depends on quantity and how much performance depends on quality, then what you have to do is you have to see how performance vary when I keep quality same and vary the quantity. If you want to know how performance depends on quality, you keep the quantity same, improve the quality, and then you exactly know with how performance depends on quality, how performance depends on quantity. It will depend on both, but on what is the rate, what is the level of dependence, what is the degree of dependence of performance on quantity and quality. This is very, very important in industries where you have some productive concept called productivity. Productivity depends on various factors. So a good manager is always interested in knowing on what factors the productivity depends more and on what factors the productivity depends less, so that he can optimize the productivity. He can see on what factors depend more, on what factors depend less. This is nothing but the natural need of partial derivatives. Your function f is a function of two variables. We are always interested in the function. How does function depends on x only? How does function depends on y only? Right. So whenever we need to know this, we go for partial derivatives. So what do you do over here? You find the derivative of f keeping y constant. You just vary x keeping y constant. You just vary x, so y has to be kept constant obviously. What does y equal to constant depend geometrically? What does y equal to constant depend geometrically? See, this is the figure which I have drawn for z equals to x square plus y square. I'll tell you what does y equal to constant tells you geometrically. See, we must understand this partial derivative geometrically also. So I have drawn this function. I told you what is the need of partial derivatives, right? Now I'll try to give you the geometrical significance of partial derivatives. Say this is the function. This is the function z equals to x square plus y square, which I have plotted over here. Y equal to, you had earlier one, this is constraint. This is the constraint on variables. You put a constraint on variables. These constraints lead to, when you join all those points which correspond to this constraint, equation of constraint, you get this paraboloid. Alright, now I have one more constraint. I put one more constraint, y equal to constant. What does y equal to constant in space represent? Y equal to constant represent the plane parallel to xz plane, where all the point has got y equal to constant, say C. So I can draw that plane. The plane will look like, say this is the plane. This is the plane, y equal to constant. I can have a point over here. I can have a point over here. That point will be 0, say 0. So this is the point. This is the on this plane, everywhere, every coordinate has y equal to constant. So set of all those points for which y is constant is given by this plane. Now I have two constraints. One, this is the constraint, right? This is also one constraint. So can you tell me the set of all those points which satisfy this also and this also? So those set of points, which obviously it will be, what will be those set of points? Those set of points will be lying on the curve of intersection of these two surfaces. What does the curve denotes? Curve denotes set of all those points for which you have this valid, set of all those points which satisfy this also. And then what does this gives you? This gives you how does f vary? Yes, geometrically this gives you how does f vary when I move along this line, when I move parallel to x-axis, when I move such that y is kept constant. This curve also gives you the same thing. Curve tells you, curve gives you a good idea. Curves give you a good idea how z is changing, when I move parallel to x-axis, when I only change x variable, when I keep y variable constant. How does this curve gives you an idea? You can say this, What is the z? Z is this for this value of x. When you move along this x-axis, what do you find? You find that z is decreasing, and then after a certain point your z is increasing. So what if this curve gives you an idea that you find the z is decreasing when you're moving along x-axis. This is getting minimum at certain point, and then it is increasing, right? It is increasing. So you can see it over here. And what is this geometrically? Geometrically, the curve gives you an idea of how does f is varying. And what is this? This is nothing but slope of the tangent. If you want to find at this point, any point, this is nothing but slope of the tangent to this curve of intersection between z equals to x square plus y square and y equal to constant. This particular quantity gives you an idea about whether f is the sign of this quantity will give you an idea whether f increases when you move along parallel to x-axis, and the magnitude tells you with what rate function increases or decreases when you are moving parallel to x-axis. What do you find over here? You find z is falling. So I can say from this point to this point, I can say that z is falling. So I can say this is negative. This is negative. Then from here onwards, you find that z is increasing, f is increasing. So you can say the sign of this dou f by dou x is positive. Now, what about the magnitude? What do you find over here? You find z is falling more rapidly over here. So you say del f by del x. So you say dou f by dou x is very much negative at these points. Dou f by dou x is very negative when I am moving over here. Dou f by dou x is becoming less negative when I come very near to this. Then over here dou f by dou x is 0. You have a constant minimum over here. Then again dou f by dou x turns positive, and it becomes more and more positive as you are moving ahead. So it gives you an idea when you are moving from here, you start your journey from here, dou f by dou x is very much negative. Means if I am moving along this at this position, as I go towards increasing x, z is falling rapidly, then z is falling slowly, then z doesn't, the fallen z is, you don't have any fallen z over here. Dou f by dou x is 0, and then you are moving from this point, dou f by dou x turns positive. It means z is increasing. Dou f by dou f is less positive over here, become more and more positive as you move ahead. So this gives you a good idea about how does f is changing when I am moving parallel to x-axis. Similarly, this gives you a good idea how f is increasing or how f is changing when I am moving parallel to, say, here I am moving parallel to x-axis. This will give you a good idea how your f is changing when you are moving parallel to y-axis, right? Similarly, right? So you can see that this also involves some kind of direction. When you're moving in the direction parallel to x-axis, this gives you an idea how f is changing. When you were moving parallel to y-axis, this gives you a good idea how f is changing. So these are also these are also a very special kind of partial derivatives. They are also very special kind of partial derivatives. They are the they are very special kind of they are very special kind of directional derivative. What does this directional derivative is? This is the directional derivative when you are moving parallel to x-axis. This is directional derivative when you are moving parallel to y-axis. When you are moving parallel to x-axis, the unit vector parallel to x-axis is going to be I, and the directional derivative will be nothing but dou f dot a, that is dou f dot I, which is nothing but this. When you are moving parallel to y-axis, your unit vector in that direction is j, and this gives you dou f by dou j. Dou f dot j, del f dot j gives you, this is a, and a is j, right? So this is nothing but this. So these are again a very special kind of partial derivatives. They are very special kind of partial derivatives. When you are moving in general directions, then your partial derivative, your directional derivative is given by this vector. Yeah, this is a vector in general, right? So a vector, this is a vector. These are two special directions. So in general, your directional derivative is given by del f dot a, and this is gradient. We call it gradient. We call it gradient. All right, this is gradient. Now see, this surface gives you a very good idea without calculating all this. If you want to analyze qualitatively, see the curve, this surface gives you a very good idea how z changes if you are moving along any direction. See, if you are moving along any direction, what do you find? If I am along this direction or this direction or this direction or all this direction along the in the domain, what do I find? For this particular case, in case of paraboloid, you find z is increasing. Z is increasing, and since this is a surface of revolution, this is a surface which is generated by revolving a parabola say y square, say z equals to x square. Say I draw a parabola, z equal to x square, z equal to x square is this kind of parabola, right? This parabola, when I rotate it about z axis, I get this particular surface. So I can say along every direction, z is increasing with the same rate. This is surface is symmetrical. This is symmetrical about z axis. This is a surface of revolution of a particular curve around z axis. In this particular case, not always, in this particular case, the way z is varying, if I am moving along say this curve or along this particular line passing through origin in this domain, what do I find is you find z is increasing in a similar fashion in all directions. When you are moving in every direction, z is increasing similarly, right? But when you are moving along some curve, the variation of z is a bit different, right? So the same thing can be studied. This is one way of studying. Drawing a surface is one way of studying how z varies. Surface makes it very clear. You are able to see it. You are able to visualize. Surface gives you a very good idea how z is increasing, how fxy increases or decreases when you are moving in particular direction. What you have to do is, if I draw this curve, what I can do is I can draw a line like this. This gives you an idea about how z is varying, right? I'll wrap this. I'll show in a clean picture, right? So if I want to find out how your z is varying when I am moving along this curve, a very simple way of getting the same thing is you just draw a line in z direction. This gives you an idea how fxy vary when you are moving along particular curve. So a surface gives you a very good idea about directional derivative. How does z varies when I am moving along this curve? I can just draw a line and see how z is varying. This is nothing but z. Alright. This is the value of z for a particular value of x and y. You can see this, right? Just like a curve gives you a very good idea how y varies by just seeing a curve for a single of one variable. You get an idea how y vary with x. Similarly, for the function of two variables, if I am able to draw the surface, I'll get a good idea how function is varying with the variation in x and y. If x and y is varying along some particular curve like this, I can draw these lines and see how fxy vary when I am moving along this curve in the domain of this function, right? See, sometimes it's not always very easy to visualize it by a surface, right? There is yet another way of getting an idea of directional derivatives, and that is through the concept of level curves. We use the concept of level curves to understand the directional derivative, to understand how the function fxy changes when you change, how this function fxy varies when you vary x and y. This is yet another way which is very, very important when you are trying to understand about some weather or you are studying geography. So you use the concept called isobars, isotherms. What do you mean by isobars? I am taking an example. Isobar is basically the curve joining all the places which are having the same pressure, right? This is the curve joining all the points on the surface which have got the same pressure. Use the concept of isobar when you are studying pressure variation, right? Pressure variation gives you a very good idea about the winds. All right. So these are all but level curves. See, if I take an example of pressure, see, I want to understand, I want to study how does pressure varies on the surface when you have, say, I am in Delhi, right? I want to know how does pressure vary when I am moving in Delhi, right? So I can say, if suppose the pressure will be a function of, say, P will be a function of x and y. X and y are the two coordinates. X and y are the two coordinates which defines the position on the place in Delhi. Your position can be defined by two variables, x and y. I can choose some origin and then I can define the position of any point on in particular region by these two coordinates, and then P will be a function of that coordinates, x and y. Pressure will be function of the place. I want to know the pressure as a function of the position. Pressure is the function of x and y. Pressure is the function of location of any point, right? The P will be function of x and y. So see, it's not very easy to get the surface representing this function. The surface can be drawn if you plot P on, if you take P on z axis, and you can plot pressure. You can join all those points such that z coordinate is given by P x y, right? But that is not always very easy. I hope you might have seen isobars. You might have seen when you listen to weather news, or if you can see the book of geography, you might have seen these curves. I'll draw those curves. These are basically isobars. These are the isobars which join all the places which are having, say, these isobar will correspond to some kind of, say, P equals to, say, 1000 bars. Say this is P equals to, I'll use different color. This is, say, P equals to 1010. This can be P equals to, say, 1020. This can be P equals to, say, 1050. This can be P equals to, say, 1070. This can be P equals to 1100. This can be P equals to, say, 1120 bars. They are all in bars. Bar is the unit of pressure. So these are the point, these are the curves joining all the places in a particular region. Say I am in Delhi, so I can say these are the curves joining all the places which has got a pressure 1000 bars. These are the points, these are the curve, this is the curve joining all the places where the pressure is 1010. These are the point joining where the pressure is 1020. This is the curve joining all the point where the pressure is 1120 bar, right? So this also gives me a very good idea about directional derivative. So you can see, this region, these curves are very close to each other. It means if I move along this direction, this is the domain x and y. It is xy plane. This is xy plane. This is the surface. And I want to know how the pressure is varying when I am moving along this. When you want to know by these curves, this curve very well tells you an idea. It gives you a very good idea about the variation of pressure when you are moving in certain directions. Say if I move in this direction, I see these isobars are very close to each other. It means the pressure is varying very rapidly. Pressure is increasing very rapidly over here. When I move in this direction, pressure varies quite rapidly when I am moving in this direction. Pressure varies quite rapidly when you are moving in this direction. The variation of pressure is quite rapid when you are moving in this direction. But what happens when I move in this direction? You see, the pressure is varying, but varying slowly, right? As you are moving in this direction, pressure varies slowly. See the gaps, there are large gaps, all right? When you move from here to here, you cover this distance, the pressure varies by just 20 bars. Whereas when you are moving a very small distance over here, pressure variation is too high. So these curves gives you a good idea about the direction, in which direction pressure varies more, in which direction pressure varies less. By seeing these curves, you get a very good idea about how does pressure vary, in which direction pressure vary more, in which direction pressure varying less. So I can say that the directional derivative of the pressure in this direction is very small. A small directional derivative of the pressure as a function is very high in this directions. So this gives you a very good idea about the flow of wind. I can say the flow of wind will be more rapid from in this direction. Wind flow from high pressure to low pressure. This is low pressure. So this is the gradient of pressure. Since the pressure variation is very high in this direction, pressure is decreasing very rapidly in this direction, right? So I can say wind is more likely to flow in this direction, more likely to flow in this direction, less likely to flow from this direction. So this gives you a very good idea about the winds flow. Once you have a good idea about the variation of pressure in associated, and so you can see it from here, the variation of pressure is not same in all directions. So here comes the importance of directional derivative in determining the flow of wind. When you come to know how does pressure varies in space, pressure varies from one point to other point. All right, so this is how we get a good idea about the directional derivative by drawing these level curves. Level curves are nothing but you draw pxy equals to constant for different constant values. For say 1000 you draw one curve, from say 1010 you draw one curve. So these are level curves. Level curves are nothing but the curves which represent p equal to constant, the curve which represent fxy equals to constant. You draw all this curve for different value of c, you get a good idea about the directional derivatives. You get good idea about the directional derivatives. For this kind of surface, I can say when you are moving in certain direction like this, the level curves will be something like this. It will be quite, say, something like this. And as you move ahead, they will get closer and closer, right? They will get closer and closer. This is not a exact circle. So they will get closer and closer. If you're moving, say, like this, it will get more closer. You can see it. Say the f is 1, f is 2, f is 3, f is 4, f is 5. What I says, initially the function, when I'm moving in any direction, initially the function is increasing less rapidly. As you move ahead, the function increases more rapidly. You can see it from here. Function increases less rapidly over here, function increases more rapidly over here. So see the 1, 2, 3, 4 and 5, you see these curves are closely spaced and they are widely spaced in the beginning. They become closer and closer as you're moving towards higher, away from this point. So these curves, they are also the level curves. Level curve corresponding to f equal to constant. So level curves gives a good idea. See, in this case, see, these are all circles. In this case, one thing I conclude that the pressure, the variation of pressure is very similar. The variation of f is similar in all directions. Similar in all directions, since this is a surface of revolution. So variation of this function is similar in all direction. But you find that as you move away and away, the f is increasing more rapidly. F is increasing more rapidly. So these level curves gives you a good idea about how the function of two variables, how the function changes when you are moving in certain direction, right? They are called level surfaces. Now this may look a bit complicated, but try to understand. This is very important, right? If you have any doubts, you can always ask me on the forums. I'll feel happy to explain any points which you don't understand, right? So this is how we study the directional derivative for the function of two variables, right? Now comes the function of three variables. What happens when you want to study the function of three variables, directional derivative in case of function of three variables? All right, see, even this pressure can be a function of three variables. Suppose it's not only a function of location of a places, but it can be a function of z also, height also, right? So in that case, pressure can be assumed to be a function of, say, x, y and z. It's not only depending on the space, the position of the point on the ground. It also depends on what is the height. What is the height? Depends on height also. If you're going more and more higher, the pressure decreases, right? So in that case, pressure can be a function of three variables. Now in this case, geometrically, I can't plot this function. I cannot plot this function as, say, f equals to p x, y, z, because I need to have four-dimensional coordinate system. But geometrically, you only have three-dimensional coordinate system. You have up to 3 dimensions. So I can't plot this because this will be a surface in four-dimensional space. So the only way to study the directional derivative in this case is to draw level surfaces. Level surface is nothing but your level surface is, if you have a function of three variable, you equate to an arbitrary constant. For different constant, you draw different surfaces. For different constant, you draw different surfaces that will give, those surfaces will give you a good idea about the directional derivatives. Like if suppose I have a function, say I have a function, I'll rub it, I'll show you how you can understand the directional derivative for the function of three variables. Suppose I have a function of three variables, f, x, y, z, as this. Suppose this is the function. All right. So if I want to study the directional derivative of such functions, then what I can do, the only way I can understand the directional derivative is to draw the level surfaces. The equation of level surface will be given by f equal to constant, that is x square plus y square minus z equal to constant. We draw this surface for different value of c. I can write this as z minus c equals to x square plus y square. I can draw the surfaces. I can draw these surfaces. So these surfaces will look like, I can draw. So these are the level surfaces. This correspond to f equal to 0. This can be, say, f equals to, this is f equals to, say, 1. This can be f equals to 2. These are how the other level surfaces. The other level surfaces. So this gives you a very good idea about the directional derivative. Suppose I want to move in this direction. This gives you how f is varying when I am moving in this direction, how f varies when I am moving in this direction. In 3 dimension you can have level surface for every constant. You can have many, sir. I have just drawn 3. So this gives you a good idea how f vary in this direction, how f vary when I am moving along this. So what do you find? You find that when you are moving perpendicular to this function, your f, the variation of f is more rapid. You can see when you are moving in perpendicular to these surfaces, the variation of f is more rapid. The variation of f is less rapid when you are moving oblique to the surfaces, right? See, I can have a level surface for this also. This can be, say, f equals to minus 1. This can be, say, f equals to minus 1, right? This can be, say, f equals to minus 2. So I can have infinite number of level surfaces, and if you want to know how this function is varying, you just draw a line in that direction and you get idea. If you are meeting the surface quite rapidly, then you say the directional derivative is more in this direction, directional derivative is less in this direction. You can say like this, right? So you just plot. If you want to find out, say, directional derivative in say this direction, what do you find? You are finding that f is falling. It means directional derivative is negative. Directional derivative is negative. It is here, if you move in, say, this direction, it is still falling, but falling less rapidly, right? It depends, right? If I'm moving, say, this direction, you see f is falling, but f is falling less rapidly. If I'm moving perpendicular to these surfaces, f is falling rapidly. Similarly, if I'm moving in opposite direction, I find f is increasing rapidly. If I'm moving in oblique direction, I see f is increasing, but increasing. The spacing between the level surfaces is very high. If I move in this direction, if I move in this direction, spacing is smaller. So if increase rapidly in this direction, less rapidly in this direction, less rapidly in still this direction. So this gives you a good idea about the directional derivatives. This gives you a good idea. These level surfaces gives you a very good idea about how does the function is changing when I am moving in a particular direction. Here the domain of these functions are in 3 dimensions. The whole 3-dimensional space is the domain of this function. So I can move in infinitely many directions. So this level surface gives you a very good idea how does function changes when you are moving in particular direction. If function increases, your directional derivative is positive. If increases very rapid, your directional derivative is very much positive, right? Magnitude gives you the rate with what the directional derivative is increasing or decreasing. The sign gives you increasing or decreasing, and the magnitude gives you the rate at which the function increases or decreases, right? So this gives you a good idea. The level surfaces gives you a good idea how about the directional derivative for the function of 3 variables, because drawing this function won't be possible geometrically, because you need 4-dimensional coordinate system where you can plot this function and they have 3 independent variables, right? So here the level surface is nothing but f equals to constant. When f is equated to a constant, for every constant you have a surface called level surface, right? This level surface will be very important in later sections. All right, so by this I end the discussion on your directional derivative. I hope you understand. If you find any difficulty, I'll feel very happy to discuss about this. This will only enhance my lecture. So you do ask question if you have any problem, because I do feel that you will have some kind of query on this particular topic. This is very bit complicated, but very important to understand. If you understand, it's good, right? So I end my lecture by this point, right? I'll in next lecture I'll discuss about the properties of gradient, right? That will be associated with the directional derivative only, right? So I'll